Introduction: a new world awaits, far beyond the boundaries of our solar system. Orbiting a faint red dwarf star in the constellation Leo lies a planet unlike any other we've discovered. Its name is K218b, and it has stirred the scientific imagination in profound ways. Unlike the distant gas giants or barren, rocky worlds we've cataloged in the thousands, K2218b offers something different, something extraordinary. It resides in the habitable zone of its star, where temperatures may allow for liquid water. Most intriguingly, recent observations have revealed the possible presence of water vapor in its atmosphere. K2118b. It's not just another data point in our growing list of exoplanets. It is a tantalizing clue in our search for life beyond Earth, a cosmic breadcrumb that could lead us to the greatest discovery of all: that we are not alone. Discovered by NASA's Kepler Space Telescope and later studied in more detail by the Hubble Space Telescope, K218b quickly became one of the most compelling exoplanetary candidates for habitability. It is roughly 8 times the mass of Earth and twice its size, placing it in a category known as super-Earths or mini-Neptunes. These types of planets do not exist in our solar system, making them especially mysterious to researchers. What makes K218b truly special, however, is not just its size or orbit, but the composition of its atmosphere. In 2019, scientists announced that they had detected water vapor using transmission spectroscopy, ionizing the starlight that filters through the planet's atmosphere as it passes in front of its host star. For the first time, we had a strong indication of a potentially habitable exoplanet with water in its skies. This audiobook invites you on a journey to explore K218b in depth, its discovery, its unique characteristics, its atmospheric chemistry, and the tantalizing questions it raises about life elsewhere in the cosmos. We'll examine how scientists detect and study such distant worlds, and what it truly means for a planet to be habitable. We will also delve into the latest findings and theories, including the possible detection of biosignature gaseous clues that may point to biological activity far from Earth. So, settle in. Let your thoughts drift across the vastness of interstellar space and prepare to uncover the secrets of a world that may just harbor the conditions for life. The journey begins now with K218b. Chapter 1: The Discovery of K2-18b. It began, as many astronomical discoveries do, with a subtle flicker of light. In 2015, data gathered by NASA's Kepler Space Telescopes, specifically from its extended K2 mission, revealed the periodic dimming of a faint red dwarf star named K2-18. These tiny dips in brightness suggested that a planet was passing in front of the star. momentarily blocking a small portion of its light. After careful analysis, astronomers confirmed the presence of an exoplanet, K2-18b, located about 124 light-years from Earth in the constellation Leo. K2218b did not initially stand out. It was just one among thousands of exoplanets identified by Kepler's tireless gaze. But as scientists dug deeper, they realized something extraordinary. K218b orbited within its star's habitable zone, the region where temperatures might allow liquid water to exist on a planet's surface. This simple fact elevated K218b from just another data point to a prime candidate in the ongoing search for life. Beyond our solar system, the confirmation of K218b's existence was only the beginning. To understand more about its nature, scientists turned to a technique called transit photometry, which involves observing the light of a star as a planet crosses in front of it. These transits provide valuable clues not just about the planet's size and orbital period, but also about its atmosphere, if it has one. In 2019, the Hubble Space Telescope was directed toward K218 to analyze the starlight filtering through the planet's atmosphere during its transit. What it revealed would soon send ripples through the scientific community. Spectral data from Hubble showed signs of water vapor in K218b's atmosphere. It was the first time that water, a key ingredient for life as we know it, had been detected in the atmosphere of a planet within the habitable zone of its star. For exoplanet researchers, this was a watershed moment. K218b was no longer just a theoretical candidate. It had measurable characteristics that made it a compelling focus for further study. Yet, K2218b remained enigmatic. Its mass and radius indicated that it was likely not a rocky world like Earth, but rather a mini Neptune, a planet with a thick atmosphere and possibly a deep ocean beneath. This made the detection of water vapor even more intriguing. Was it floating high in hydrogen-rich clouds? Or did it hint at a deeper, potentially life-supporting layer hidden far below? The discovery process also showcased the collaborative nature of modern astronomy. Scientists from around the world combining data from Kepler, Hubble, and ground-based observatories worked in tandem to piece together the story of this distant world. Their efforts highlighted how our understanding of the universe is constantly evolving, and a tireless curiosity about what lies beyond. K2-18b, single quotes, as discovery, marked a turning point. It reminded us that the universe is vast and full of surprises, and that sometimes a tiny dimming of starlight can lead to revelations of cosmic importance. For the first time, we had a distant world with conditions that might be favorable for life. And we had the tools to study it in ways never before possible. As we continue our journey through this audiobook, we will peel back the layers of what makes K2 be such a fascinating world. But it all started with a flicker-on, almost imperceptible blink of light from a quiet star in Leo that whispered a message across the galaxy. I am here. Chapter 2. The Host Star. Red Dwarf K2-18. 2. Understand a planet. We must first understand its star. In the case of K2-18b, that star is K2-18. A relatively small and faint red dwarf located in the constellation Leo, though modest in appearance. K2-18 holds the key to the environment that surrounds its orbiting planet. The star's characteristics, its size, temperature, luminosity, and activity shape everything about K2-18b's climate and potential to support life. K2-18 is classified as an M dwarf, or red dwarf, a type of star that is cooler and smaller than our Sun, with only about 40% of the Sun's mass and a fraction of its luminosity. Red dwarfs like K2-18 burn through their fuel slowly, granting them astonishingly long lifespans. While our Sun has a lifespan of roughly 10 billion years, a star like K2-18 could burn steadily for tens or even hundreds of billions of years. This longevity makes red dwarfs especially intriguing targets in the search for habitable planets. But longevity is not the only advantage, because red dwarfs are dim. Their habitable zones, the region where liquid water could exist, are much closer to the star than in systems like ours. K2-18b, for example, orbits its star at a distance far closer than Mercury orbits the Sun, completing a full revolution in just 33 Earth days. Despite this proximity, the planet's surface could still maintain temperate conditions due to the star's lower energy output. Yet this closeness also brings challenges. Red dwarfs are known for their stellar flare sudong, eruptions of high-energy radiation that can bathe nearby planets in potentially harmful ultraviolet and X-ray radiation. If K2-18 is particularly active, its flares could strip away a planet's atmosphere or sterilize its surface. However, the level of activity among red dwarfs varies widely, and K2-18 appears to be on the calmer end of the spectrum, especially compared to other flaring stars like Proxima Centauri. Astronomers have been studying K2-18 using photometric and spectroscopic data to determine just how volatile it is. So far, the evidence suggests that it may not be a frequent flaring star, which is good news for K2-18b's prospects. A relatively stable stellar environment would allow any atmosphere on the planet to persist over long timescales, possibly long enough for life to develop if other conditions are right. The light from K2 to 18 also plays a crucial role in the study of K2-18b's atmosphere. When the planet transits the star, starlight filters through the planet's atmosphere and becomes imprinted with spectral signatures. These subtle fingerprints help scientists identify molecules such as water, vapor, methane, and hydrogen without the steady light of K2-18. We wouldn't be able to learn nearly as much about its distant companion. Interestingly, red dwarfs like K2-18 are the most common type of star in the Milky Way galaxy. They vastly outnumber stars like our Sun, which suggests that planets orbiting red dwarfs may also be extremely common. If many of these planets reside in their stars' habitable zones, then the conditions for life might not be rare at all. They might be abundant. Understanding K2-18 is more than a side note in the story of K2-18b. The calm demeanor of this small, distant star makes it one of the most promising hosts we know for a potentially habitable world. It teaches us that sometimes quiet stars can nurture extraordinary possibilities, and as we look deeper into K2-18b's composition and environment, we carry with us the understanding that its fate and, perhaps, its ability to harbor life is inextricably tied to the subtle, steady glow of its parent star. Chapter 3: What makes K2-18b so unique? In a galaxy filled with billions of stars and an ever-growing catalog of exoplanets, what sets K2-18b apart? Why has this distant world over 124 light-years away captured the attention of scientists, astronomers, and dreamers alike? The answer lies in a rare and compelling combination of characteristics that make K2-18 be not just another planet, but a beacon in the search for life beyond Earth. First, there is its location in the habitable zone of its star cosmic sweet spot, where temperatures could allow liquid water to exist. While many exoplanets reside in similar zones, most either lack atmospheres or orbit unstable stars. K2-18b, however, orbits a relatively calm red dwarf and has a substantial atmosphere that appears capable of sustaining complex chemical processes. This delicate balance alone is rare. Then there is its size and mass. K2-18 billion is what scientists call a super-Earth, or a mini-Neptune, a planet larger than Earth but smaller than the ice giants Uranus and Neptune, with about 8 times Earth's mass and roughly 2.6 times its radius. K2-18b falls into a mysterious in-between category. Planets of this size do not exist in our own solar system, making them difficult to study and even harder to classify. Are they rocky with thick atmospheres? Are they gaseous with deep oceans? K2218b sits on this boundary, inviting us to redefine what it means for a planet to be Earth-like. But the uniqueness of K218b goes even deeper. In 2019, scientists announced that they had detected water vapor in its atmosphere. Discovery made through spectral analysis using the Hubble Space Telescope. This was the first time that water had been identified in the atmosphere of a planet located in its star's habitable zone. That alone would have made headlines. Yet what made the finding even more astonishing was the implication that K218b might host liquid water beneath its dense atmosphere. Possible requirement for life as we know it. The detection of water vapor suggested that K218b's atmosphere is rich in hydrogen, which raises important questions. Hydrogen-rich atmospheres are believed to be more conducive to retaining heat, potentially creating a greenhouse effect that could warm the planet's surface or its underlying ocean. At the same time, such an environment could also shield life from harmful radiation, depending on the atmospheric layers. This possibility opens the door to a new class of potentially habitable worlds. Hycean planets, planets with hydrogen-dominated atmospheres and global oceans. Beneath K2-18b, single quotes, as possible, identity as a Hycean world is revolutionary. These planets could be far more common than previously thought, and their existence challenges traditional ideas about where life might thrive. Life may not require a solid, rocky surface at all. It might emerge in high pressure, high temperature, aquatic environments beneath thick, insulating atmospheres. If K2-18b turns out to be such a world, it could expand the scope of our search for life across the galaxy. Its orbit also offers observational advantages. Because it transits its star as seen from Earth, we can study its atmosphere during these transits. This alignment allows telescopes like Hubble and the James Webb Space Telescope to analyze starlight as it filters through the planet's gaseous envelope, providing rich information about its chemical makeup. Few exoplanets offer such an ideal setup for atmospheric characterization. Even the star it orbits plays into its uniqueness. K2-18 is a relatively quiet red dwarf, less prone to the violent flares that often strip nearby planets of their atmospheres. This stability increases the chances that K2-18b's atmospheric conditions have remained intact over long time scales, allowing any potential biospheres to develop undisturbed in many ways. K2-18b is a cosmic bridge linking the familiar and the unfamiliar, the known and the possible. It challenges our assumptions and invites us to think more broadly about what a habitable world might look like. In its clouds may lie not only water, but also the answers to some of humanity's most profound questions. Are we alone? Could life take root in conditions vastly different from Earth's? Uniqueness is often measured by how much something changes our perspective. And in that sense, K to 18 billion is not just a distant world, is a turning point in our understanding of the universe and our place within it. Chapter 4: The Habitable Zone Explained. The concept of the habitable zone is central to modern astronomy, especially in the search for life beyond Earth, often referred to as the Goldilocks zone. It's the region around a star where conditions are just right, not too hot, not too cold for liquid water to potentially exist on a planet's surface. Since life, as we know it, depends on water, the habitable zone is often the first place scientists look when assessing a planet's potential to host life. 4K218b. This distinction is especially important. Its orbit around the red dwarf star, K2-218, places it squarely within that coveted zone. But what does that really mean? The boundaries of a habitable zone depend on the type of star at the center. For our Sun, the habitable zone stretches roughly from Venus to just beyond Mars. But for a smaller, cooler star like K2-218, that zone is much closer in. Because red dwarfs emit less energy than stars like our Sun, their planets must orbit more tightly to receive a similar amount of warmth. K218b, for example, completes one orbit in just 33 Earth days. Yet it receives a similar amount of stellar radiation as Earth. Dose from the Sun being in the habitable zone suggests that K218b could maintain surface temperatures where liquid water might exist, an essential ingredient for life as we understand it. However, this is not a guarantee. A planet's ability to sustain water also depends on other factors like its atmosphere, pressure, albedo, reflectivity, and internal heat. K218b's thick, hydrogen-rich atmosphere complicates the picture, but also opens up fascinating possibilities. The concept of the habitable zone has evolved over time. Originally, it was thought to be a narrow range where Earth-like conditions might exist. But as we've discovered more about exoplanets and alternative life-supporting environments, the definition has broadened. Some scientists now include planets that might have subsurface oceans, like Jupiter's moon, Europa, or thick atmospheres that create temperate conditions at high altitudes. As with the hypothetical cloud cities of Venus. In this expanded view, K2-218 billion becomes even more interesting. Its size and atmosphere suggest it may not have a solid surface like Earth's. Instead, it could possess a deep global ocean with temperatures regulated by a dense atmosphere. Even if the surface pressure is too high for humans, microbial life might find a niche in the upper atmospheric layers, or deep beneath an ocean insulated from harmful radiation. Another crucial factor is the stability of the star. Red dwarfs, though long-lived, are often known for intense flaring activity that can strip a planet's atmosphere or bombard it with dangerous radiation. Fortunately, K218 appears to be a relatively quiet star, which improves the odds that any atmosphere on K218b has remained intact. One thing to keep in mind is that the habitable zone concept is Earth-centric. It's based on what we know about life on our planet. But life elsewhere might be more adaptable than we imagine. There may be forms of life that thrive in environments radically different from our own, rendering our definition of habitable just one small piece of a much larger cosmic puzzle. Still, the habitable zone remains an essential guidepost. It gives us a way to narrow the vast number of exoplanets down to a manageable list of promising candidates. And within that list, K218b stands out not only because of where it is, but because of what we've already detected in its atmosphere. K218b is one of the few exoplanets we've found that combines the two critical ingredients for potential habitability. It resides in the right orbital zone, and it shows evidence of water vapor in its skies. This double discovery makes it a prime target for telescopes like the James Webb Space Telescope, which are designed to look deeper, clearer, and farther than ever before. The habitable zone is more than just a calculation. It's a promise that in the darkness between stars, there are worlds that might echo our own. And K218b is one of the brightest beacons we've found so far. Chapter 5: Atmospheric Clues. Water vapor detected. The discovery of water vapor in the atmosphere of K218b marked a pivotal moment in the search for habitable exoplanets. It wasn't just a technical triumph, it was a philosophical awakening. For the first time, we had strong evidence of a world outside our solar system, located in the habitable zone of its star, where water vapor, one of the fundamental ingredients of life, was detected. But how did we discover something so delicate, so distant, hiding in the veil of an alien sky? The answer lies in a powerful technique called transmission spectroscopy. When a planet transitsor passes in front of its host star, as seen from Earth, a fraction of the starlight passes through the planet's atmosphere before reaching our telescopes. This light becomes imprinted with the chemical signatures of the molecules present in that atmosphere. By carefully analyzing this filtered light, scientists can deduce the composition of the air enveloping the planet. In 2019, data collected by the Hubble Space Telescope revealed a remarkable pattern in the light from K2-18b's transits. Embedded in the infrared wavelengths was a spectral fingerprint that matched water vapor. The finding sent waves of excitement through the scientific community. Not only had we identified water in the atmosphere of a planet more than 124 light-years away, but that planet also orbited within its star's habitable zone. This was not just a statistical anomaly or a modeling quirk. The signal was strong and consistent. Multiple teams of researchers independently confirmed the result using different analytical methods. The scientific consensus formed quickly. K2-18b has water vapor in its skies. The implications were profound. Water vapor implies a planetary environment with temperatures and pressures that allow water to cycle between its gaseous and potentially liquid states. On Earth, this cycle sustains life, drives weather, and moderates climate. Could something similar be happening on K2-18b? However, excitement was tempered by the need for caution. K2-18b is a large planet, about 8 times Earth's mass and over twice its size. These proportions suggest it may have a thick, hydrogen-rich atmosphere, possibly making it more similar to Neptune than to Earth. The surface conditions beneath such an atmosphere might be extremely hot and pressurized. Life as we know it to survive. But this is where imagination and science intersect. Even in a high-pressure, hydrogen-dominated world, life could find a way, especially in stratified atmospheric layers where temperatures and pressures are more Earth-like. The detection of water vapor doesn't confirm life, but it opens a door we had only dreamed of walking through. More tantalizing still, recent models suggest that K2-18b might possess a deep liquid ocean beneath its atmosphere. In such a scenario, water vapor could rise from this ocean, circulate through the atmosphere, and condense into clouds mirroring Earth's hydrological cycle on a planetary scale. Another exciting possibility is that K2-18b belongs to a new class of exoplanets known as Hycean worlds. These are ocean-covered planets with hydrogen-rich atmospheres that may offer a stable, life-supporting environment beneath their thick clouds. If K2-18 billion is such a planet, the water vapor detected could be part of a vast oceanic world, teeming with unseen potential. The detection also underscores the importance of advanced space telescopes. Hubble provided the first hints, but the James Webb Space Telescope is expected to take this investigation further, offering high-resolution spectra that could reveal not only water vapor, but other vital gases like methane, carbon dioxide, and even possible biosignatures like dimethyl sulfidin, organic molecule associated with microbial life on Earth. The sky of K218b, rich in vapor and mystery, reminds us how much we still have to learn. It whispers across the light years that the building blocks of life may not be unique to Earth, that the processes that shaped our atmosphere might be mirrored in worlds far beyond our own. Water is the common thread of biology as we know it, and in the veiled atmosphere of a distant exoplanet, we may have just found the first drop in a cosmic ocean. Chapter 6. What is a super-Earth? Among the thousands of exoplanets discovered to date, a mysterious class has emerged, one that doesn't exist in our own solar system. These are the super-Earths, planets larger than Earth, but significantly smaller than Neptune. K218b belongs to this intriguing category. Understanding what a super-Earth is and what it isn't is essential to grasping what makes K218b such a compelling world. The term super-Earth refers to a planet's mass and size, not necessarily its composition or habitability. In general, super-Earths range from about 1.5 to 10 times the mass of Earth, with radii up to about 2.5 times that of our planet. K218b sits firmly within this range, being about 8.6 times more massive than Earth and roughly 2.6 times larger. In radius, these proportions give K218b a curious identity. It's significantly larger than Earth, but not large enough to be considered a gas giant like Neptune. And because we don't have any planets of this size in our own solar system, our understanding of their structure and conditions is based entirely on indirect measurements, theoretical models, and comparative data from many other exoplanets. Some super-Earths are thought to be rocky, like an oversized version of Earth, possibly with continents, oceans, and atmospheres. Others, like K218b, appear to have thick hydrogen or helium atmospheres and may even harbor deep global oceans beneath them. These differences have led scientists to further categorize super-Earths into subclasses, such as Hycean planets, ocean worlds with hydrogen atmospheres, mini-Neptunes, gas-rich, less likely to be habitable, and true rocky super-Earths, solid, planets with thinner atmospheres. The ambiguity in categorizing K218b illustrates the challenge. Its density, which is determined from its mass and volume, suggests that it's not entirely rocky. Instead, it may have a solid core surrounded by a thick envelope of volatile gases. Alternatively, it could be an ocean world with a deep water layer beneath a dense atmosphere, conditions that, under the right circumstances, could be compatible with life, which can have dramatic effects on atmospheric retention and surface conditions. A denser atmosphere could trap heat more efficiently, making the planet warmer than its orbital distance alone would suggest. However, it also raises questions about habitability. Would the pressure be too high for life to thrive at the surface, or might life exist in more temperate layers of the atmosphere, or in suboceanic regions shielded from extremes? One reason super-Earths have captured the imagination of astronomers is their sheer abundance. Statistically, they appear to be one of the most common types of planets in the galaxy. If even a small fraction of them reside in habitable zones and have life-friendly conditions, the number of potentially life-supporting worlds could be enormous. K218b gives us a fascinating case study in this emerging category. It challenges our understanding of habitability by existing outside the template set by our solar system. It's not an Earth twin, but it's not a gas giant either. It exists in a kind of planetary twilight zone, big, heavy, cloud-covered, and mysterious dot as scientists develop better tools and models. They're beginning to ask deeper questions. Can super-Earths host Earth-like ecosystems? Are their oceans too deep, their pressures too intense, or their atmospheres too alien? Or are they, perhaps, even better suited for life than Earth is more stable, longer-lived, with protective clouds and nourishing chemistry? We don't yet have the answers. But super-Earths like K218b have shown us that the universe is far more diverse and potentially hospitable than we ever imagined. In the silence between the stars, there may be countless super-Earths, each holding secrets in their skies, oceans, and cores. And if we're lucky, one of them might be more than just a planet. It might be a home. Chapter 7. Life as we know it. The essential conditions. When we speak of life elsewhere in the universe, we inevitably begin with a familiar template life as we know it. This means carbon-based organisms that rely on water as a solvent, require a source of energy, and exist within a specific range of temperatures, pressures, and chemical environments. These conditions are based entirely on Earth's biology, but they serve as a logical starting point in our exploration of distant worlds like K2-18b. So, what exactly are the essential ingredients for life as we know it? And does K218b offer any of them? The most fundamental requirement is liquid water. On Earth, every known form of life depends on it. Water serves as a medium for chemical reactions, helps regulate temperature, and allows molecules to move and interact. This is why the detection of water vapor in K218b's atmosphere generated so much excitement. It suggests that liquid water could exist in clouds as rain or in vast subsurface oceans. The second key ingredient is a source of energy. On Earth, this comes primarily from the sun, but life can also thrive around hydrothermal vents deep in the ocean, drawing energy from chemical gradients instead of sunlight. K218b orbits within the habitable zone of a red dwarf star, receiving a consistent supply of stellar energy. Additionally, if K218b has a thick atmosphere and a dynamic interior, it might also retain heat from gravitational or geothermal processes, offering alternate energy pathways for life. Next comes organic chemistry, the presence of carbon-based molecules capable of forming complex structures such as proteins, nucleic acids, and lipids. On K218b, the discovery of water vapor, along with hints of methane and carbon dioxide in the atmosphere, is a promising sign. These compounds often participate in biological or pre-biological processes and can serve as building blocks for more complex chemistry. Stability is another important factor. Life needs time to emerge, adapt, and evolve. This requires a relatively stable environment over millions or billions of years. Fortunately, K218 star appears to be relatively quiet for a red dwarf, less prone to violent flares that could strip a planet's atmosphere or sterilize its surface. The star's low luminosity and extreme longevity also suggest that K218b could remain in the habitable zone for a very long time, potentially giving life a vast window in which to develop. Atmospheric pressure and temperature also play key roles. Too much pressure and biochemical processes could be crushed before they begin. Too little and vital gases may escape into space. On K218b, the presence of a thick hydrogen-rich atmosphere suggests high surface pressures, but not necessarily beyond the range where microbial life could exist. Some regions of the atmosphere might offer a sweet spot with moderate temperatures and pressures, much like those on Earth's surface or in its oceans. Of course, many unknowns remain. Is there a solid or liquid surface beneath the clouds of K218b? If so, is it made of rock, ice, or water? Could life exist suspended in atmospheric layers, like potential microbes in the clouds of Venus? These are the questions scientists hope to answer with more data from the James Webb Space Telescope and future missions. Interestingly, the definition of life supporting is beginning to shift. Standard researchers are increasingly open to the idea that alien life may thrive under alien conditions, environments that are extreme by our standards, but stable and rich enough in chemistry to allow evolution. Still, until we encounter such life directly, life as we know it remains our best guide. And from that perspective, K218b is one of the most promising candidates we've ever found. It has water, vapor, possible energy sources, the right location, and a stable environment, crucial elements in the grand cosmic recipe. It reminds us that the conditions that gave rise to us may not be unique, that the chemistry of life could echo in clouds far above an ocean of unknown depths, beneath a sun no one has ever seen. Chapter 8: Biosignatures. The hunt for alien chemistry in the vast cosmic search for life. Detecting a planet in the habitable zone with water vapor in its atmosphere is only the beginning. The true prize, the signal that could change the course of science and history, is the detection of biosignatures, chemical traces in a planet's atmosphere that may indicate the presence of life. But what exactly are biosignatures? And could K218 be whispering signs of alien biology across the void? A biosignature is any detectable feature, usually a molecule or pattern, that is difficult to explain by purely non-biological processes. On Earth, gases like oxygen, O, ozone, Ov, methane, Hycean, and carbon dioxide, CO, produced or sustained by living organisms. Their presence, especially in certain combinations, can be a strong indicator of biological activity. However, interpreting these signals isn't easy. Many of the same gases that life produces can also arise from abiotic processes, volcanic eruptions, chemical reactions in the crust or atmosphere, even stellar radiation. That's why scientists look for combinations of gases that are in a state of chemical disequilibrium, a state that should not exist unless there is an ongoing process replenishing one or more components. For example, the simultaneous presence of oxygen and methane is difficult to maintain without some form of active metabolism to produce them both. In 2023, new studies using early data from the James Webb Space Telescope, JWST, suggested the possible presence of methane and carbon dioxide in K218b's atmosphere. Even more provocatively, scientists reported a tentative signal of a molecule called dimethyl sulfide, DMS, a compound on Earth that is produced almost exclusively by living organisms, particularly marine plankton. Though this detection is far from confirmed, it raises the possibility that some form of life, or a biological like chemistry, might be at work far beyond our solar system. If DMs or similar complex molecules are confirmed in K218b's atmosphere, it would represent a historic breakthrough, the strongest biosignature ever detected on an exoplanet. But the scientific community remains cautious. Spectral signals can be noisy and ambiguous, and models must be carefully calibrated to avoid false positives. Adding to the complexity is the fact that K218b has a hydrogen-rich atmosphere. This type of environment is very different from Earth's nitrogen atmosphere, and the chemical pathways are not yet fully understood. Some scientists propose that hydrogen-dominated atmospheres may enhance the detectability of certain biosignatures, while others warn that exotic chemistry in such environments could mimic lifelike signals. This is where context becomes essential. To assess biosignatures on K218b, scientists must consider a wide range of factors: the star's radiation, the planet's temperature and pressure profiles, the composition and layering of the atmosphere, and the long-term stability of detected molecules. Only by piecing together this complex puzzle can we determine whether the chemistry we see is the result of life, or simply the natural behavior of alien geophysics. Future telescopes will play a crucial role in this process. While JWST has given us an unprecedented glimpse into K218b's skies, coming missions like LOVOIR, HABEX, or the extremely large telescope ELT on Earth will push the frontier even further. These instruments may be capable of directly imaging exoplanets, capturing detailed spectra that could reveal new biosignature candidates or even patterns of change over time that hint at active ecosystems. It's also important to remember that biosignatures might not look like the ones we know. Life on K218b, if it exists, could be utterly unlike Earth life, perhaps based on different molecules, operating at different energy scales, or evolving in high-pressure, low-light, oceanic environments. That's why some researchers advocate for a broader definition, not just looking for Earth-like biology, but for any sign of persistent, organized chemical processes that defy geological explanation. K2-18b may or may not host life, but it is already helping to refine the tools and methods we use to search for it. It has become a training ground for the science of astrobiology, forcing us to grapple with the challenge of interpreting faint chemical signals across unimaginable distances. In that way, the hunt for biosignatures is more than just a scientific quest, it's a philosophical one. It forces us to ask, what is life? How do we recognize it when we see it? And are we prepared to understand a biology that may have never evolved on Earth? If K218b carries the fingerprints of life, they are written in vapor and light, waiting to be read. And with every spectrum, every signal, we come closer to answering a question older than science itself. Are we truly alone? Chapter 9. A closer look. K218b's atmosphere. When we imagine distant exoplanets, we often think of alien landscapes, oceans, mountains, deserts, or icy plains. But for many worlds, like K218b, the surface may be forever hidden from view. What we can study instead, with increasing clarity, is their atmosphere, the veil of gases that surrounds them and holds the secrets to their climate, chemistry, and even their potential to host life. K2-18b. Single quotes, atmosphere is unlike anything we know in our solar system, based on its size, mass, and observed spectra. Scientists believe it is likely hydrogen-rich, meaning it contains large amounts of hydrogen and helium, with traces of other molecules like water vapor, methane, and carbon dioxide. This composition makes K2-18 be a member of a curious and poorly understood category of planets that blur the line between rocky worlds and gas giants. The hydrogen-dominated nature of the atmosphere is significant for several reasons. First, hydrogen molecules are light and buoyant, which means the atmosphere is likely to be extended and fluffy compared to Earth's. This enhances our ability to study its starlight filtering through a puffier atmosphere, carries stronger molecular signals, making it easier to detect specific gases. The detection of water vapor was the first major breakthrough, achieved using the Hubble Space Telescope. Subsequent analyses have hinted at the presence of methane and carbon dioxide (CO2) molecules that are critical for understanding the planet's chemistry and potential habitability. If confirmed, these molecules suggest the presence of carbon-based cycles, possibly maintained by atmospheric processes, geology, or even though far less likely biology. More recently, early data from the James Webb Space Telescope, JWST, provided a deeper look into K2-18b's atmosphere. The enhanced sensitivity of JWST's instruments allows scientists to measure infrared light with far greater precision than before. One of the key findings from these observations is the possibility of a stratified atmosphere, where different gases are concentrated in distinct layers, much like Earth's own atmosphere, with its troposphere, stratosphere, and beyond. This layering could create microclimates within the atmosphere, including regions with temperatures and pressures that are relatively mild and stable. In theory, such niches could be hospitable to microbial life, especially if water vapor condenses into clouds or droplets at certain altitudes. Some researchers have even speculated that cloud-borne ecosystems, similar in spirit to Earth's airborne microbes, could exist in these intermediate layers. However, K2-18b's atmosphere may also be immensely deep and pressurized, meaning that any ocean or surface beneath could be subjected to crushing forces and extreme heat, whether solid ground exists at all. Instead, the planet may have a supercritical Osuna state of matter, where water exists as a dense, steamy fluid that is neither liquid nor gas, flowing beneath an oppressive blanket of high-pressure gases Understanding such extreme environments requires complex atmospheric modeling. Scientists simulate everything from the planet's chemical reactions to radiative transfer of heat and light to cloud formation and dynamics. These models help researchers interpret the subtle signals we observe and predict how various gases might behave under alien conditions. One of the great puzzles is whether the atmospheric composition of K218b is primordial, left over from the planet's formation, or evolved through geological or potentially even biological processes. If the atmosphere has remained largely unchanged since the birth of the planet, it might tell us about the early conditions of the planetary system. But if it has changed, it could reflect ongoing internal activity or external influences like stellar radiation. Does another exciting aspect of K218b's atmosphere is the potential detection of biosignature gases like dimethyl sulfide DMs. Although this finding remains highly tentative, on Earth, DMs is almost exclusively produced by marine microorganisms. If this molecule is truly present on K218b, and no known non-biological process can account for it under those conditions, it would be one of the most compelling pieces of evidence for life ever discovered. Yet the scientific community remains cautious. For every possible biosignature, there is a need to rule out false positives, non-living processes that might mimic biological activity. That's why understanding the context of K218b's atmosphere is crucial. The interplay of temperature, pressure, stellar activity, and chemical cycles must all be considered. What is certain is that K218b's atmosphere is rich in mystery. It holds not only the clues to the planet's composition and climate, but possibly even hints of biology in its layered haze of hydrogen and vapor. We are beginning to see the contours of an alien environmental world that challenges our assumptions, expands our perspective, and invites us to look deeper in the folds of K218b's sky. Science and imagination meet, and with every observation, we inch closer to unlocking the secrets it holds. Chapter 10: Challenges of Habitability on K218b. While K218b offers tantalizing signs of potential habitability, it also presents a host of challenges that complicate the picture. Understanding these obstacles is crucial in evaluating whether this distant world could truly support life as we know it, or if its environment is too extreme and alien. One of the primary challenges is the planet's size and gravity. Being about 8 times more massive than Earth, K218b exerts a much stronger gravitational pull. This gravity likely influences atmospheric retention, making it possible to hold onto a thick envelope of gases, mainly hydrogen and helium. But a denser atmosphere also means higher surface pressure, which could create harsh conditions at the planet's base, possibly crushing any form of life or precluding the existence of a solid surface altogether. Next, there is the question of temperature. Although K218b orbits in its star's habitable zone, the presence of a thick, hydrogen-rich atmosphere may induce a strong greenhouse effect. This can lead to temperatures much higher than expected based on orbit alone. High temperatures might prevent liquid water from existing on the surface or ocean, pushing it instead into a superheated, supercritical state, unsuitable for life as we know it. Another concern is stellar activity. While K218 appears less active than many red dwarfs generally emit intense stellar flares and high-energy radiation that can strip away planetary atmospheres or damage emerging life. A flare strong enough could erode atmospheric layers, change chemical compositions, posing a significant threat to Habitability.K2-18b. Single quotes as tidal locking is also a potential challenge, given its close orbit around a small star. It's likely that one side of the planet constantly faces the star, while the other remains in darkness. This condition can cause extreme temperature differences between the day and night sides, possibly leading to violent weather patterns and climate instability. However, some models suggest that a thick atmosphere could redistribute heat. Mitigating these effects, the composition and thickness of the atmosphere add further complexity. A hydrogen-rich atmosphere may make it difficult for light to penetrate, limiting the energy available to the surface or ocean beneath. Additionally, thick cloud layers could block radiation needed for some biochemical processes, although they might also shield the planet from harmful stellar emissions. We must also consider the unknown nature of K218b's surface or ocean. It's unclear whether a solid surface exists or if the planet is covered by a deep, high-pressure ocean beneath layers of gas. The pressure and temperature conditions at these depths may be inhospitable, or they may harbor unique niches where life could develop in forms radically different from terrestrial organisms. Finally, the lack of direct observational data remains a significant hurdle. Much of what we know comes from remote sensing techniques that infer atmospheric composition and planetary characteristics indirectly. This leaves room for uncertainty, speculation, and revision as new data arrives from telescopes like JWST. Despite these challenges, K2218b remains a compelling target precisely because it pushes the boundaries of what we consider habitable. The planet forces us to rethink the delicate balance of conditions required for life and expands the horizons of astrobiology. Could life exist in forms adapted to high pressures, thick atmospheres, or even floating in the clouds? Might exotic biochemistries thrive where Earth life would perish? The search continues, with each challenge inspiring new questions and deeper exploration. K218b may not be an Earth twin, but it is a reminder that habitability is a spectrum, broad, complex, and full of surprises. Chapter 11. Comparing K218b to other exoplanets. In the vast gallery of discovered exoplanets, K218b stands out not because it is the most Earth-like, but because it resides at the intersection of possibility and mystery. To fully appreciate its uniqueness, it's useful to compare it with other notable exoplanets that have captured the imagination of scientists and the public alike. Let's begin with TRAPPIST-1e, part of the famous TRAPPIST-1 system, located about 40 light-years away. This system includes 7 rocky planets orbiting an ultra-cool red dwarf star, with at least 3 of them, including TRAPPIST-1e, in the habitable zone. Unlike K218b, TRAPPIST-1e is closer in size to Earth and is likely to be rocky, with more moderate atmospheric pressure. However, its host star is far more active than K218, emitting frequent flares that may threaten atmospheric retention. K218b may be larger and less Earth-like in structure, but its quieter star gives it a potentially more stable environment. Another compelling comparison is Proxima Centauri b, the closest known exoplanet to Earth, orbiting our nearest stellar neighbor just 4.2 light-years away. Like K218b, it orbits in the habitable zone of a red dwarf and may support liquid water. But again, stellar activity is a concern. Proxima Centauri is a known flare star capable of releasing bursts of radiation that could strip away atmospheres or damage surface life. While K218b is much farther, it might offer a more hospitable long-term climate. Then there's LHS-1140b, a rocky planet also in the habitable zone of a red dwarf, with a radius about 1.7 times that of Earth and a mass approximately 7 times greater. It appears to have a dense atmosphere and possibly even liquid water on the surface. Compared to K218b, LHS-1140b is likely more terrestrial. But again, we have less evidence of its atmospheric composition, whereas K218b has confirmed water, vapor, and potentially methane and carbon dioxide. Kepler 2 to b. Once a headline maker, is a super-Earth in the habitable zone of a Sun-like star. While it shares similarities with K218 billion in size and orbit. It lies at a far greater distance, 600 light-years, away and lacks detailed atmospheric data. K218b, by contrast, has been studied more extensively thanks to its transits and favorable proximity, relatively speaking, allowing telescopes like Hubble and JWST to investigate its atmosphere directly. What about GJ1214b? This planet is often referred to as a mini Neptune and has many similarities to K218b. In terms of size and atmospheric thickness, GJ1214b was one of the first exoplanets with a detectable atmosphere, but its composition remains largely opaque. High-altitude clouds or hazes have obscured much of its chemistry. K218b, with its clearer atmospheric signals, offers a better opportunity for studying specific molecules. Hycean planet Kandatsa, new class of potentially habitable exoplanets, characterized by hydrogen-rich atmospheres and deep global oceans. K218b is currently the leading candidate for this classification. Its size, atmospheric composition, and habitable zone orbit position it as the prototype of a world that might sustain life in exotic ways beneath thick skies, within warm ocean depths, or among floating cloud layers. What makes K218b so fascinating, in comparison to these worlds, is the balance of extremes. It's neither a typical rocky Earth clone, nor a giant gas world. It has a thick, extended atmosphere, but with detectable water vapor. It orbits a red dwarf, but not an especially violent one. It's large and dense, but not so much that we can rule out the presence of oceans or temperate layers. It's this in-between nature, not too big, not too hot, not too cold, not too quiet, not too active, that makes K218 be such a powerful subject of study. It sits on the frontier of our understanding, bridging the gap between known and unknown, Earth-like and alien, in the ever-growing cosmic catalog. K218b is not just a number, it's a benchmark, a world by which others are measured and through which new ideas are born. Chapter 12. The role of the James Webb Space Telescope in the unfolding story of K218b. One character looms large, a planet, nor a star, but a telescope. Space has become the key to unlocking the secrets of distant worlds like K218b. Without it, our understanding of this exoplanet would remain shrouded in uncertainty. With it, we are beginning to peer into the alien skies of another world with unprecedented clarity. Launched in December 2021, JWST is the successor to the Hubble Space Telescope, but with far more powerful instruments designed specifically for studying the infrared spectrum. This is the range of light most useful for detecting chemical signatures in planetary atmospheres, including water, methane, carbon dioxide, and other possible biosignatures. K218b is a perfect target for JWST. It's relatively close in astronomical terms, about 124 light-years away. It transits its host star, meaning it passes in front of the star from our point of view. During these transits, some of the starlight filters through the planet's atmosphere, carrying with it spectral fingerprints of the gases that surround the planet. This is exactly the kind of signal JWST was built to decode. In 2023, JWST turned its powerful eyes toward K218b, and the results were immediate and striking. Using its near-infrared spectrograph, a near-infrared imager, and slitless spectrograph, NIRIS, JWST detected water vapor, methane, and carbon dioxide in the planet's atmosphere molecules that are critical to understanding the chemistry and potential habitability of the planet. These observations added depth and precision to the earlier findings made by the Hubble Space Telescope. But the most exciting possibility was something entirely new: a tentative detection of dimethyl sulfide DMs, a molecule that, on Earth, is produced almost exclusively by living organisms, especially by marine phytoplankton. If this detection is confirmed, it would be the strongest candidate for a biosignature ever found beyond Earth. The key word, however, is tentative. JWST's findings must be carefully validated with further observations. Be subtle and prone to misinterpretation due to noise, atmospheric interference, or instrument sensitivity. Yet the precision and stability of JWST's instruments allow for repeated fidelity measurements, meaning that future transits of K218b could confirm or refute the presence of DMs and refine our understanding of the planet's atmospheric structure beyond individual molecules. JWST can also provide temperature profiles, pressure gradients, and even estimates of cloud cover on exoplanets like K2218b by measuring how the atmosphere absorbs and emits infrared radiation at various altitudes. Scientists can build complex models that simulate the climate and chemistry of the planet with surprising detail. Another powerful tool JWST brings to the table is the ability to observe the thermal emission of the planet itself, not just the starlight passing through its atmosphere. This can help distinguish between different atmospheric compositions and even reveal how heat is distributed across the planet's surface or atmosphere, especially if the planet is tidally locked. JWST also opens the door to long-term monitoring. By observing K218b during multiple transits, scientists can track changes in the atmosphere over time searching for variations in cloud density, gas concentrations, or even seasonal patterns. These time-based studies could hint at dynamic processes that are geological, meteorological, or just maybe biological in nature. The telescope's role extends beyond K218b. It is also surveying other potentially habitable worlds, expanding our understanding of atmospheric diversity across the galaxy. But K218b remains one of its most important targets, a proving ground for the next generation of planetary science and astrobiology. In many ways, JWST is not just an instrument. It's a new kind of a lens through which we see the universe in ways that were impossible before. It bridges the gap between speculation and data, between curiosity and discovery. And as it continues to study K218b and its alien sky, we may find that the most powerful tool in our search for life isn't a spacecraft or a sensor, but the ability to look deeper, with clarity, into the unknown. Chapter 13. Could life exist in a hydrogen-rich atmosphere? When we envision the atmosphere of a habitable world, our instinct is to look for something Earth-like. Nitrogen, oxygen, perhaps a dash of carbon dioxide and water vapor. But what happens when the dominant gas is hydrogen? Could life, especially life, or even thrive in such an environment? This is the critical question posed by K218b, whose atmosphere is believed to be hydrogen-rich, a trait shared with gas giants like Neptune and Jupiter. While such atmospheres may seem hostile to biology at first glance, the reality is more complex and more fascinating. Let's begin with the basics. Hydrogen H is the lightest and most abundant element in the universe. On Earth, it's found primarily in water, not as a dominant atmospheric gas, but on exoplanets like K218b, where gravity is stronger and planetary formation conditions differ. Hydrogen can remain abundant in the upper atmosphere, forming thick layers that extend far into space. The presence of a hydrogen-rich atmosphere raises several key implications for potential habitability. Enhanced greenhouse effect hydrogen is surprisingly effective at trapping heat. Even a relatively thin layer of H can warm a planet significantly by allowing infrared radiation to circulate and be absorbed. On K218b, this could create temperate conditions at certain altitudes, even if the planet as a whole is larger and farther from its star than Earth. Atmospheric scale height, because hydrogen is so light, it creates a puffier atmosphere, one that is more extended and layered. This is advantageous for astronomers as it makes spectral analysis easier. But from a biological perspective, it may also create stratified zones, where temperatures, pressures, and chemical concentrations vary dramatically with altitude. Some of these layers may offer stable, habitable conditions, possible life zones. In the clouds, if the lower atmosphere or surface is too hot or pressurized for life, scientists speculate that life could exist suspended in upper atmospheric layers. On Earth, microbial life has been found drifting in our atmosphere, surviving on water vapor, sunlight, and airborne nutrients. A similar phenomenon might be possible in the hydrogen-rich skies of K218b, especially in regions where water vapor condenses into clouds. Energy and chemistry, hydrogen is a highly reactive gas and plays a central role in many biochemical processes. Certain Earth microbes, such as methanogens, use hydrogen as a key source of energy, combining it with carbon dioxide to produce methane. If such metabolisms can arise in an Earth-like context, could they also evolve in hydrogen-dominated environments? Researchers are already exploring the possibility of alternative biospheres lifeforms adapted to alien conditions. For example, theoretical models suggest that hydrogen atmospheres might support slower but more stable biochemistry, potentially creating environments where life evolves differently, but no less robustly. Protection against radiation. One might expect that a hydrogen-rich world orbiting a red dwarf star would be bombarded by radiation. But hydrogen atmospheres can offer significant shielding from ultraviolet and cosmic radiation, especially if thick and stable. This may protect the lower layers or cloud zones where life could take hold. However, challenges remain. High pressure and low density in the deepest parts of the atmosphere may make chemical bonding and molecular interaction more difficult. Additionally, a hydrogen-rich environment could limit the availability of oxidants, compounds that act as energy sources. In many terrestrial metabolisms, without oxygen or other strong oxidants, alien life would need to operate on very different chemical cycles. There's also the issue of detectability. Life in a hydrogen-dominated atmosphere might not produce familiar biosignatures like oxygen or ozone. Instead, we may need to look for other indicators, such as unusual ratios of methane, ammonia, or complex sulfur compounds like the tentative detection of dimethyl sulfide DMs. On K2-18b, recent research into Hycean worlds, new theoretical class of exoplanets combining hydrogen-rich atmospheres and global oceans has reignited interest in these types of planets. K2218b may be the archetype of such a world. Its potential to host habitable conditions in a hydrogen atmosphere challenges long-standing assumptions and suggests that life might arise in more diverse environments than we previously imagined. In the end, the question is not whether hydrogen-rich atmospheres are Earth-like. They clearly are not, but whether life could adapt to the conditions they offer. And if nature has shown us anything, it's that life is resilient, innovative, and astonishingly flexible, perhaps on a distant world. Beneath a sky of hydrogen and vapor, something unfamiliar is breathing quietly, invisibly, waiting to be found. Chapter 14: Ocean Worlds and the Possibility Beneath the Clouds. As we peer through the veils of K-18b's atmosphere, one question captures the imagination more than any other. What lies beneath the clouds? Could there be an ocean vast, dark, and alien, stretching across an entire planet beneath its thick, hydrogen-rich sky? This idea is not fantasy. It's rooted in science, and it's one of the most intriguing possibilities. K2218b may be what scientists call an ocean world, a planet covered entirely by liquid water with no exposed landmasses, encased under high-pressure gas layers. Ocean worlds are not just speculation. Even within our own solar system, several moons like Europa, Enceladus, and Ganymede are believed to harbor subsurface oceans beneath their icy crusts. These oceans may be warmed by tidal forces or internal heat, and they offer tantalizing locations for potential extraterrestrial life. K218b may represent the next step in this line of thinking, an exoplanet-scale ocean world, far more massive than any moon, and possibly covered by an enormous global sea. But conditions on K21ATB are far more extreme than those of Europa or Enceladus. If an ocean exists there, it likely begins far beneath the upper atmosphere, where temperatures and pressures are high enough to keep water in a supercritical state of phase of matter that is neither liquid nor gas, but something in between. This exotic form of water could flow with tremendous density, behaving like a deep, steaming fluid that coats the planet in silence and mystery. Above this ocean might lie layers of high-altitude clouds composed of water droplets, vapor, and haze, much like the clouds of Earth, but suspended in a very different atmosphere. These clouds could serve as both a protective barrier from radiation and a dynamic environment for potential chemistry. If the temperatures in some of these atmospheric layers fall within habitable ranges, say between 0 degrees Celsius and 100 degrees Celsius, then both oceanic and aerial life zones become theoretically possible. It's important to note that if life exists in such a world, it would not resemble Earth's surface ecosystems. Instead, it might be more like the deep biosphere found in our own ocean's microbial, resilient and adapted to extreme environments. On Earth, life thrives around hydrothermal vents on the seafloor. where light never reaches and the environment is rich in minerals and chemical energy. A similar setting could exist in K218b's deep waters. But how could we ever know? The answer lies in the molecular whispers that escape the ocean and rise into the sky. Gases like methane, carbon dioxide, ammonia, or even complex organics could be released from the ocean, mix with the atmosphere, and rise into layers where telescopes like JWST can detect them. This upward migration of molecules might carry clues about the chemistry and possibly the biology taking place beneath the clouds. One of the most exciting concepts in recent research is that Hycean planets, like K218b, could be better suited to life than Earth-like planets in certain ways. Their thick atmospheres protect against radiation. Their oceans may be stable over billions of years, and their hydrogen-rich envelopes could amplify the visibility of biosignature gases, making detection from afar more likely. Still, enormous questions remain. Does K218b have a solid seafloor, or does the pressure simply increase until water blends into a slushy core of ice and rock? Is the ocean in contact with any minerals that could fuel chemical reactions? And can life emerge in the high temperature, high pressure gradients found deep below? We don't yet know the answers, but we are beginning to ask the right questions. The idea of ocean worlds invites us to expand our definition of habitability. Life might not need continents or sunshine. It might not need air or photosynthesis. It might arise in the dark, in the depths, under pressure, quiet, persistent. An alien K2-18b, hidden beneath its clouds and hydrogen, could be a planet-wide sea, humming with the potential for life. And if we listen closely enough, it may one day tell us what lies in its unseen depths. Chapter 15. The Hycean Planet Hypothesis. In recent years, a new category of exoplanet has emerged on the edge of scientific imagination and evidence. The Hycean planet. The name is a blend of hydrogen and ocean, and these worlds are characterized by two defining features: a thick, hydrogen-rich atmosphere and a vast, planet-wide ocean beneath. They are neither rocky like Earth nor gaseous like Neptune. Instead, they occupy a unique space in between. And K218b is currently the prime candidate for this extraordinary planetary class, the Hycean planet. Hypothesis challenges many of our long-held assumptions about where life can arise. For decades, the search for habitability was dominated by the hunt for Earth-like conditions: solid ground, breathable air, and temperate climates. But Hycean worlds suggest that life may be more adaptable and more widespread than we imagined. Let's explore what makes these planets so compelling. First, Hycean planets are larger than Earth, but smaller than Neptune, typically ranging from 1.5 to 2.5 times Earth's radius. K218b falls comfortably within this range. These planets likely have deep oceans covering their entire surfaces, possibly hundreds of kilometers deep, far more vast and pressurized than Earth's deepest trenches. Above these oceans is a hydrogen-rich atmosphere, which behaves very differently from the nitrogen mix we're familiar with. Hydrogen allows for stronger greenhouse warming, meaning Hycean planets can remain temperate even when they orbit farther from their stars. This expands the so-called habitable zone and creates more opportunities for life-friendly conditions. Hycean worlds can also come in several varieties. Theoretical models describe dark Hycean planets, which are tidally locked, with only the night side maintaining habitable conditions. Cold Hycean planets located farther from their star, but warmed by a thick atmosphere, and hot Hycean planets, where habitable conditions exist in cooler cloud layers despite high surface temperatures. K218b could fall into more than one of these subtypes. It's a warm, possibly tidally locked world, but with a deep atmosphere that may host temperate atmospheric zones or shield an internal ocean. These layers could create environments with Earth-like temperatures and chemical stability, key ingredients for life. One of the most important implications of the Hycean hypothesis is that such planets may vastly outnumber true Earth analogs. According to some estimates, Hycean-type worlds could make up a significant fraction of the exoplanets discovered by missions like Kepler. This means the most common type of habitable world in the galaxy may not look like Earth at all, but like K2-18b. Even more intriguing, Hycean planets may enhance our ability to detect biosignatures. The extended atmospheres of these planets make it easier for telescopes like JWST to analyze chemical content. This increased detectability, combined with the possibility of microbial life in cloud decks or oceans, makes Hycean worlds a goldmine for astrobiology. Of course, the hypothesis is still in its infancy. We have yet to confirm the ocean beneath K2-18b's clouds, or to fully understand the stability of its atmosphere. We also don't yet know whether life can truly adapt to high pressures, low oxidant availability, and potential chemical constraints of such environments. But the beauty of the Hycean hypothesis is that it asks the right questions. It expands the framework of habitability beyond Earth-like planets and opens up entire new categories of worlds to serious consideration. It suggests that life may not be rare, may simply be unfamiliar. K218b, with its potential, ocean, hydrogen, skies, and biosignature hints, is more than just a mystery. It is a possible blueprint for a new class of habitable world type that could fill the galaxy. If the Hycean hypothesis is correct, then our search for life has just begun. Universe may be far more welcoming than we ever dared to hope. Chapter 16. How common are worlds like K218b? If K218b truly is a Hycean planet, warm, water-rich, and wrapped in a hydrogen-dominated atmosphere, then it may not be a rare cosmic outlier, but a representative of one of the most common types of planets in our galaxy. Understanding how frequent such worlds are helps us frame one of the most profound questions in science. Is life likely to exist elsewhere? The search for exoplanets began in earnest only in the mid-1990s. Since then, the catalog of confirmed exoplanets has grown to over 5,000, with thousands more awaiting verification. Most of these discoveries come from space telescopes like Kepler, TESS, and Spitzer, which use the transit method, detecting the tiny dips in brightness when a planet crosses in front of its host star. As data from these missions accumulated, an unexpected trend emerged. Planets between the sizes of Earth and Neptune, often called sub-Neptunes or mini-Neptunes, were extremely common. These planets are 1.5 to 3 times the size of Earth, and K218b, with its radius roughly 2.6 Earths, falls squarely within this category. In fact, these sub-Neptune-sized planets are more numerous than gas giants like Jupiter or Saturn, and even more common than true Earth-sized planets, at least in the range our current instruments can detect. This suggests that the most typical planet in the Milky Way may not be rocky and dry, but thickly veiled in gas and potentially hiding deep oceans below. The Kepler mission estimated that up to 50% of Kakwa Sun-like stars may host planets in the habitable zone that are smaller than Neptune. That doesn't guarantee they're all Hycean worlds, of course, but it tells us that planets similar in size and temperature to K218b are not rare. And with upcoming missions like the Plato Observatory and ground-based surveys using the extremely large telescope ELT, we're likely to uncover even more of them. Another factor contributing to their abundance is the prevalence of M-dwarf stars, also known as red dwarfs. These small, cool stars make up nearly 3/4 of all stars in the galaxy, and their compact, dim nature makes them ideal targets for transit observations. Many planets found around these stars fall into the size and temperature range associated with the Hycean category. K218b orbits one such red dwarf star, and while not all M-dwarf planets are suitable for life. Many suffer from stellar flares or tidal locking. Some, like K218b, orbit more quiet and stable stars, improving their habitability prospects. What's particularly interesting is that, while Earth-like planets with thin atmospheres and exposed surfaces may be harder to detect due to their smaller sizes and weaker signals, Hycean-type planets with extended atmospheres are easier to observe and characterize. Their large atmospheric scale heights amplify their spectral signals, allowing telescopes like JWST to measure their chemical fingerprints with greater clarity. In this way, K218b is not just a planet of interest, it is a gateway. It's teaching us how to study planets that are neither entirely rocky nor fully gaseous, but something in between. And the more we learn, the more we realize that this middle ground may be the rule, not the exception. This realization changes the odds. If life can exist on worlds like K218b, and if such worlds are as common as the data suggests, then habitable environments may number in the billions across the Milky Way. That doesn't guarantee that life has emerged elsewhere, but it means the stage is set over and over again. The cosmos, it seems, is filled with planets that are not quite Earth, not quite Neptune planets, wrapped in mystery, floating silently in hydrogen skies, and perhaps, just perhaps, teeming with life beneath oceans no eye has yet seen. Chapter 17. What would alien life on K218 be like? As we inch closer to understanding the physical conditions of K218b, a more profound and imaginative question begins to emerge. What would life on such a world actually look like? If life exists on K218b, how would it survive, function, and evolve in an environment so utterly different from Earth? The short answer is, it would likely be nothing like us. But the long answer invites us into the deep interplay between biology, chemistry, and planetary physics of space, where alien life is not just possible, but plausible in forms we are only beginning to imagine. To begin, let's consider the environmental context. K218b is a super-Earth or mini-Neptune with a thick, hydrogen-rich atmosphere, possibly covering a vast, high-pressure ocean. Temperatures may range from extreme at the surface or core to mild and temperate at mid-atmospheric layers, the so-called habitable altitudes. This stratified structure offers multiple potential biospheres. One, aerial life in the atmosphere. One possibility is cloud-borne organisms, living in the temperate zones of the atmosphere, perhaps akin to Earth's microbes that drift in our skies. These life forms could exist in microscopic droplets, feeding on atmospheric chemicals like hydrogen, methane, or ammonia. Their metabolism might resemble Earth's methanogens or sulfur-producing bacteria, but adapted to float, absorb nutrients from gas phase reactions, and withstand high radiation levels. Some scientists envision balloon-like microbial colonies, inflated with lighter gases to maintain buoyancy, or even colonial chains of microscopic life that slowly drift with wind currents, reproducing in bursts when conditions align. This cloud-based ecosystem might be transient, appearing when temperatures and water vapor levels allow, and disappearing when conditions shift, like microbial blooms in Earth's oceans. Only aloft in a hydrogen sky. B2. Life in the ocean depths. If K218b has a deep, global ocean beneath its atmosphere. That ocean could be a second domain for life. Pressures might be intense, and the water could be in a supercritical state. But life may still find a way, just as it does near Earth's deep-sea hydrothermal vents. There, life survives without sunlight, feeding instead on chemical energy from reactions between water and rock. On K218b, if any rocky core interacts with the ocean, similar geochemical processes known as serpentinization could provide the energy needed for primitive life. These life forms might not resemble any Earth organism. They could lack traditional cells or DNA, using instead novel solvents, membranes, or genetic systems. Their metabolisms could revolve around hydrogen chemistry, using carbon dioxide and hydrogen to generate energy in a form unknown to us. And if they evolved over billions of years, they might form entire ecosystems beneath the sea, invisible to our telescopes, but silently shaping the chemistry of the atmosphere. Above, 3 hybrid forms: ocean, atmosphere, life. There's also the theoretical possibility of life that bridges both realms, like jellyfish analogues that drift between layers, or microbial spores carried by evaporative processes from sea to sky and back again. On Earth, bacteria can travel from the ocean's surface into the atmosphere via aerosols. Why not on K218b? Over time, such organisms might evolve traits for survival in extreme transitions, resisting pressure changes, enduring brief radiation bursts, and exploiting any short-lived niches created by storms, chemical gradients, or seasonal shifts. Now, what would such life look like? It depends entirely on the chemistry and pressures they've adapted to. Without visible light, or with only dim red light from their star, photosynthesis might use infrared energy or rely entirely on chemical sources. Organisms might be dark, translucent, or highly reflective, evolving to absorb or deflect energy efficiently. They may not have eyes but sensors for pressure, magnetism, or chemical gradients. They might move not with legs or fins, but with gas jets, osmotic pulses, or even magnetically driven currents. And most provocatively, they might be completely microbial, with no multicellularity, no structures, and no visible footprint, just complex, adaptive chemistry, embedded in every droplet of water or gas molecule. If intelligent life evolved, that is, an enormous, if its existence would be shaped by entirely different evolutionary pressures. Would they build technology beneath the sea? Use sound instead of light? Think in patterns shaped by chemistry instead of symbols and language? These are questions we cannot yet answer. But the speculation is not without purpose. It guides design of our instruments, the search for biosignatures, and even the way we interpret data from distant ATMOSPHERES.K2-18b. If it exists, need not resemble Earth's biology at all. The universe may be full of strange and alien creatures, some microscopic, some cloud-bound, some swaying silently beneath oceans of boiling hydrogen. And one day, a molecule, a spectrum, or a signal might whisper their presence across the light years, reshaping forever what we understand as alive. Chapter 18: The Future of Exoplanet Exploration, Our Understanding of K218b, and of the thousands of other exoplanets discovered so far, is only the beginning. What we know today, fragmentary spectra, rough masses, and theoretical compositions, will soon be transformed by the next generation of telescopes, missions, and ideas. The coming decades promise a revolution in how we explore the cosmos and how we search for life beyond Earth right now. Space-based observatories like the James Webb Space Telescope, JWST, are at the forefront with its powerful infrared vision. JWST has opened the possibility of measuring atmospheric compositions, detecting key gases, and even identifying potential biosignatures like methane, carbon dioxide, and water vapor. K218b's atmosphere is already yielding secrets thanks to this incredible instrument. But JWST is just the beginning. In the 2030s, space agencies plan to launch even more specialized telescopes. One of the most anticipated is LUVOIR, Large UV Optical Infrared Surveyor, a proposed NASA mission that would be capable of imaging Earth-like exoplanets directly and analyzing their atmospheres for oxygen, ozone, and surface vegetation signatures. Another is HABEX's Habitable Exoplanet Observatory, designed to search for small, rocky planets and characterize their potential habitability with unprecedented precision. Both Love War and Habix would use starshades or coronagraphs to block the overwhelming glare of a host star, revealing the faint light reflected by an orbiting planet. This direct imaging approach would allow astronomers not only to detect a planet's presence, but to see it as a point of light, analyze its color, temperature, and even surface features. Meanwhile, on Earth, next-generation ground-based telescopes will play a critical role. The extremely large telescope ELT in Chile, the 30-meter telescope TMT in Hawaii, and the Giant Magellan Telescope GMT are all under construction or planning. With mirror sizes many times that of current observatories, they will be able to study exoplanet atmospheres and weather patterns from the ground with remarkable clarity in parallel. Missions like TESS, Transiting Exoplanet Survey Satellite, and Plato, Planetary Transits and Oscillations of Stars, a European Space Agency mission, are continuing the search for new worlds, especially those orbiting bright, nearby stars. The closer and brighter the star, the easier it is to analyze its planets. These missions will expand our catalog of potentially habitable worlds and provide targets for more powerful observatories. One of the boldest ideas in development is interstellar exploration. Projects like Breakthrough Starshot aim to send tiny, light-powered spacecraft to nearby stars like Proxima Centauri, a fraction of the speed of light. Though still in the conceptual stage, such missions suggest a future where we don't just observe distant worlds from afar, we visit them, even if only with tiny, robotic eyes. Technological progress is not the only challenge. We must also refine our scientific frameworks. As we encounter increasingly diverse exoplanets, Hycean, oceanic, rocky, icy, and more, we need new models of habitability, biology, and atmospheric chemistry. The question is no longer just, is this planet like Earth? But could life survive here in this set of conditions? And with each new discovery, the definition of habitability evolves. Once, it was based solely on distance from a star. Now, it includes atmospheric composition, pressure, magnetic shielding, and even stellar activity. Future models may incorporate completely novel factors like tectonic activity, ocean salinity, or the availability of trace metals. Importantly, the future of exoplanet exploration is deeply collaborative. Space agencies, universities, private foundations, and international teams are all part of this unfolding story. Observatories will share data, cross-verify detections, and build cumulative models of alien systems. It will be a global effort. The search for life beyond Earth belongs to all of us. And what about public engagement? As data becomes more accessible, and citizen science projects expand, ordinary people, students, hobbyists, dreamers will increasingly play a role in identifying and characterizing distant worlds. Programs like Planet Hunters have already allowed volunteers to find new exoplanets missed by algorithms. In the future, the next K218b might be discovered not by a space agency, but by a curious mind on the other side of the world. K218eb has taught us that worlds unlike our own may still be profoundly habitable. But it has also shown us something deeper, that with the right tools, patience, and curiosity, the universe will begin to reveal its secrets. The coming years will bring sharper instruments, bolder missions, and deeper questions. But with each step, we edge closer to that moment of profound revelation, the day we confirm, beyond doubt, that we are not alone. Chapter 19: Ethical Implications of Discovering Life Beyond Earth. In science fiction, the discovery of alien life is often portrayed with spectacle, flashing lights, strange languages, grand declarations. But in the real universe, the first contact might come in a far subtler form, a chemical signature in the atmosphere of a planet like K218b, suggesting that life exists there, unseen and unreachable. And when that moment comes, it won't just be a scientific event, will be an ethical turning point for humanity. The implications of discovering life beyond Earth, microbial, aerial, aquatic, or otherwise, run deep. They challenge not only our sense of identity, but our responsibilities, our place in the cosmos, and how we behave toward life, even when it lies 124 light-years away. Let's begin with the moral significance of alien life. If we detect life on K218b, it may be completely unlike anything on Earth. Different chemistry, no DNA, no cells as we know them. But it would still represent something profoundly rare, a second genesis, a separate origin of life in the universe. That fact alone would elevate even the simplest organism to extraordinary value, just as we recognize the importance of protecting fragile ecosystems on Earth. Would we not have a moral obligation to preserve alien life, even if we never touch it? This is not a hypothetical concern. If, in the far future, we develop the technology to send probes or even crewed missions to distant exoplanets, what principles should guide us? Should we land on a world we suspect may harbor life? Should we alter its atmosphere or oceans to suit our needs? Should we terraform or instead protect it from contamination? These are questions with no clear precedent, and yet the decisions we make in coming decades regarding planetary protection, bioethics, and interstellar exploration may lay the foundation for how we answer them. There's also the issue of indirect harm. Suppose we detect atmospheric signatures on K218b that hint at life such as methane combined with carbon dioxide. In the rush to understand it, would we treat that planet purely as a resource, a data mine, or as a living system deserving of restraint and reverence? And if one day we could reach it, would our very presence destroy the delicate chemistry that sustains life there? Even robotic exploration could pose risks. Earth microbes are notoriously hard to eliminate completely from our spacecraft. A single contaminant might wipe out an entire alien ecosystem accidentally and invisibly. This is why the field of astroethics is emerging as a vital complement to astrobiology. It asks hard questions. What rights, if any, do alien life forms have? Should discovery confer stewardship or dominion? Can a planet be sacred simply because it harbors life? But the ethical implications don't stop at K218b. If we find life there, then life may be common, and the universe is likely teeming with it. That realization would transform human identity. For millennia, we've asked if we're alone. A single signal, one atmospheric whisper, could answer that question forever. Such a discovery could reshape religion, philosophy, politics, and even economics. What role would Earth play in a universe where life is abundant? Would nations compete for access to life-harboring worlds, or cooperate to protect them? Would the idea of life itself expand beyond biology, beyond Earth, beyond imagination? Even more provocatively, if microbial life exists on K218b, then more complex life might evolve elsewhere. Civilizations, cultures, minds. The ethical frontier would then expand once more from microbial life to intelligent life. How would we act if we knew someone knew something was watching from the stars? And finally, we must consider how discovering life beyond Earth could change our treatment of life on Earth. Would it inspire humility and awe? Would we become better stewards of our own fragile biosphere, knowing that life is not a cosmic fluke, but a precious thread in a vast, interconnected universe? Or would the knowledge of life beyond us deepen our divisions over who owns space, who speaks for Earth, who decides what comes next? There are no easy answers, but one thing is certain: the ethics of the cosmos are already upon us. The discovery of alien life, whether on K218b or any other world, will be more than a scientific moment. It will be a test of our values, our foresight, and our maturity as a species. And in that sense, it's not just about what we find, it's about who we become when we find it. Chapter 20. A new perspective on our place in the universe. Standing beneath the stars, we've always wondered, what lies beyond. Are we alone? Is Earth unique? Are we an exception or a reflection of what the cosmos has to offer? The discovery and study of K218b has not answered all these questions, but it has begun to shift how we ask them. Once, the search for life beyond Earth focused on finding another Earth. We imagined blue oceans, green forests, breathable skies. But K218b has shown us that the truth may be far stranger and more wondrous. Wrapped in hydrogen, cloaked in clouds, and possibly covering a dark, planet-wide ocean, it's not Earth-like. And yet, it may be habitable. It may even be alive. That realization changes everything. It means that habitability is not a narrow path, but a broad landscape. Life does not demand Earth's exact recipe. It may rise in hydrogen skies, drift in clouds, thrive in chemical oceans, or hide in alien pressure zones beneath distant stars. What matters most is not how familiar a planet looks, but how it works. K218b, 124 light-years from Earth, now represents a new kind of frontier. It is not just an object of study. It is a symbol of how far we've come and how much we've yet to learn. It reminds us that the cosmos is not silent, only distant, that life may be not rare, but resilient, adaptable, tenacious, and startling in its creativity, and that our tools, questions, and imaginations are finally catching up to the mysteries around us. But most of all, K218b offers us a mirror not of our planet, but of our perspective. It shows us that Earth is precious, not because it's the only possible home for life, but because it's the one that gave rise to us. And it challenges us to grow, to become explorers, protectors, thinkers, and listeners, not just for ourselves, but for the universe we are just beginning to meet as we look into the hydrogen-rich skies of K218b. We are not simply looking for life, we are asking the universe who we are, and the answer, when it comes, will not just be about them. It will be about us.